This Pythagorean identity, sine squared of x plus cos squared of x equals 1, is probably the most commonly used identity in all of trigonometry. First, we're going to show that it's true from first principles. I also should mention, though, that sine squared x is how we write sine of x all squared. It means sine of x times sine of x. So recall that in any angle x, sine of x means opposite over hypotenuse. So sine of x would be opposite of hypotenuse, square that. And cos of x is adjacent over hypotenuse, square that. And we're trying to show that that equals 1. So with a little simplification, some algebra, we get opposite squared over hypotenuse squared equals adjacent squared over hypotenuse squared. We have a common denominator, so we can write this as opposite squared plus adjacent squared over hypotenuse squared. Now remember that from any right angle triangle, if this is our angle x, this would be opposite, adjacent, and hypotenuse. By the Pythagorean theorem, opposite squared plus adjacent squared has to equal the hypotenuse squared. So I'm going to replace opposite squared plus adjacent squared with hypotenuse squared. And now you can see that hypotenuse squared divided by hypotenuse squared is 1. So this is very, very important. It's going to be used over and over and over again as an identity when you're substituting and trying to simplify trig equations, identities, and etc. From this identity, we can very quickly and easily derive this one. If we start with sine squared x plus cos squared x equals 1, and we divide everything by cos squared x, each term divided by cos squared x, sine squared x over cos squared x, if you remember, sine over cos is tan, so this would be tan squared of x. Of course, cos squared divided by cos squared is just 1. And then 1 over cos squared, well, we know that 1 over cos is equal to secant. So 1 over cos squared would be secant squared x. And we've just shown that this identity is true. By the way, these are called the Pythagorean identities because they are a direct result of the Pythagorean theorem, and also they look like the Pythagorean theorem. You have something squared plus something squared equals something squared in each case. Something squared plus 1 squared equals secant squared. This one we can also derive starting with sine squared x plus cos squared x equals 1, the first identity. This time dividing everything by sine squared x, each term divided by sine squared x. This, of course, is 1. Cos squared over sine squared, that should be a plus sign, that's a plus sign, is cotangent squared x, and 1 over sine is cosecant, so cosecant squared x, and now we've proven this trig identity. So these three are considered the Pythagorean identities, but this one is the one you're going to use the most. We're going to use these identities along with the other identities that you've already learned to simplify trigonometric expressions. These are some very, very key tools that you can use in simplifying trig expressions. The first thing that's really helpful is to write anything other than sine or cosine in terms of sine or cosine using their reciprocal identities. Use the Pythagorean identities to substitute for squared functions. Factor the expression, either a common factor or factor it as a trinomial, and you can also find a common denominator. So for this first example, I have to simplify cosecant x over cotangent of x. So I'm going to use this first tool, which is to write both of these trig ratios in terms of sine and cos. I know that cosecant of x is 1 over sine x, and I know that cotangent of x is cos x over sine x. This is what it means to write everything in terms of sine and cos. How can I write this in terms of sine or cos? It's 1 over sine. How can I write this in terms of sine and cos? It's cos over sine. Now it's just some simple algebra. To divide, you invert and multiply, so this becomes 1 over sine x times sine x over cos x. As I invert that, sines cancel. I'm left with 1 over cos of x, which of course is secant x. So I've taken this expression and simplified it to this expression.